In this video, we're going to continue our discussion from section 4.1. And before you watch this, please make sure that you've looked over the theorem on the previous page of the module on Blackboard. And you can also open up your textbook to that theorem in the section. What I want to do in this video is discuss how to prove the first property of the theorem. And what we're trying to do here is show that when we multiply a vector times 0, we get the 0 vector. When we were just dealing with real numbers and Rn, this sort of thing is fairly obvious because we're just multiplying numbers by 0. But in a more abstract setting, we might have to worry about it more. So this requires a proof. So what I'm going to do is start with this side of the equation, the right side of the way it's written in the theorem. And I know from the definition of my vector space that if I add a vector and the negative of the same vector, I get 0. So 0 is equal to a vector plus its negative. And the vector I've chosen here is 0 times v, so what appears on the left side. But at the moment, it's not by itself. It has its negative along with it. So we have to do a little bit more work. Let's focus in on this 0 here. 0 is, of course, the number 0, and it's equal to 0 plus 0. That's not saying anything new. But what this lets me do is distribute using one of the distributive properties. This is the 8th property of the vector space, if you're keeping track. I can distribute my vector over scalar addition to get 0v plus 0v, and the negative of 0v has just come along on each step. But now on this one, I have an extra 0v that can cancel off with the negative of 0v. And when you cancel off these two, that leaves you with 0 times the vector v. And that's what we wanted to end up with. So going through the equality, we have the 0 vector is equal to 0 times v. So one thing that you have to be careful about when you're doing proofs like this is to make a distinction between the 0 vector and the 0 scalar. So the way I've done that here is by putting a bar above the 0 to represent the 0 vector, and the other zeros without bars are scalars. So these are all scalar multiplication down here. So we're going to skip over part 2 of the theorem because that's going to be on your homework, and we're going to go on to part 3. And the proof to part 3 is in your textbook, and I'll let you read it there. But it relies on this fact, which is sort of mentioned in passing in your textbook, but not proven. So let me write it out. Let V be any vector space, and let lowercase v with a bar on it be a vector in our vector space V. Then the negative of v, which we use this notation for, just a minus sign written next to v, the negative of v is unique. So that means there's not more than one negative of v, and if we find two negative v's, or two things written differently, and we know that they're both negatives of v, then they're actually the same to begin with, which is what we have to do to prove part 3 of this theorem. We have to show that something is the negative of v. So let's do this proposition, and I'll let you read the proof of the theorem on your own. So in the proposition, what I'm going to do is suppose that I have two different negatives of v. So both u and w are vectors, and they're both negatives of v. So what that means is if I have v plus u, I get 0, and if I have v plus w, I get 0. And what I want to do is show that these are actually the same to begin with. So u is equal to w. And here's how we go about that. I'm going to start with my vector u, and I'm going to add 0 to it. But I can make use of this equation up here. V plus w is equal to 0. So instead of writing 0, let's write v plus w. And now I can rearrange the parentheses. So this is the associative property of addition. This is property 4 of the vector space if you're keeping track. But u plus v, we know, is 0. So instead of writing u plus v, let's just put down 0. And then 0 plus w, that's just w. So working through the equation, I see that u, the vector, is equal to the vector w. So my two negatives of the vector v were actually the same vectors all along. Okay, so now that you've seen this proposition, you should take a look at the proof for part 3 of the theorem in your textbook.